Okay, finally, folks, let's take a look at the graph, because this graph is slightly different from the previous graph. X-axis, still ions dissociated per molecule, but now you see the axis goes not just to 1, but to 3, because we have 1, 2, 3 distinct protons that can be lost. 1, 2, 3. pH, the y-axis, still the same. But you'll see, instead of just having one buffering region, there are now 3 buffering regions. Okay, buffering region 1, buffering region 2, buffering region 3. Each of these buffering regions is kind of flat, because that's demonstrating the pH isn't changing. There's 3 midpoints. Each of these midpoints is going to show you the pKa for that proton. Finally, there are 3 equivalence points. The equivalence points you'll see if you go to the bottom, the x-axis, directly aligns with when a proton is completely lost. So the first equivalence point is when that first proton at 1 completely lost. Second equivalence point you'll see aligns with 2 protons lost, so the next proton is completely lost, and the same for the third. Okay. Now let's think about each buffering region and what's happening to the various protons at different pHs. Let's start at a pH of 1. So let's find pH 1 on this graph. It's right here. What does the molecule look like at a pH of 1? Well, as I've shown you at the top right here, even though my head is kind of covering this, there are the 3 protons that we can lose. Let's quickly just write down the pKa's for these protons to keep these in mind, and I'll draw a little star next to each of these pKa's. Okay. So the first pKa is, let's call it 2.1. pKa2, we already know that. That's one that we've been talking about. That's 6.8. And what's the third pKa? Let's call that 12.2. We'll round. So these are each of the pKa's. Right now we're talking about what's happening to the molecule at a pH of 1. Well, at a pH of 1, if we drop this down to the x-axis, we can see that this first proton is almost entirely kept. It hasn't dissociated really at all. So what should the molecule look like at this pH? Well, if the first proton has not really dissociated at all, it should look something like this. It should have all of its protons. Okay. Now, let's take the next scenario and think about it. What's happening at a pH of 4? So first things first, let's find pH of 4. Bring it over to the curve. Here we are, pH of 4. At pH of 4, drop this down to the x-axis, we have completely lost, because we're at 1, a single proton. What about the other 2 protons? Well, we're only at 1, we're not really past 1 at all, so protons 2 and 3 have been kept. So at this point, the molecule has lost a single proton and should look like that. And I'll just draw these little arrows so you know what's happening. Finally, a pH of 9. Let's think about what's happening at a pH of 9. So there's 9. Drop it down. We are now at 2. The second proton has been completely lost if we are at 2, but nothing should have happened to the third one. So now, oops, that's not a P. Now the molecule should have lost both the first proton and the second proton almost entirely. So now the molecule at a pH of 9 should look like that. So these are things that I want us to start thinking about. What's the pH compared to the pKa? Quick heads up, folks, that if you go to Top Hat, and if you scroll to the handouts folder, there's going to be kind of 2 handouts that I want you to keep an eye out for. One handout is called Common pKa's. It's just a list of some common pKa's that in no way would you have to memorize, but might be cool to look through. More importantly though, I have a handout called pKa and acid and conjugate base forms in biochemistry. It's going to show you some different pKa's that are important, and it's going to give you some rules about protonation and deprotonation when comparing pH and pKa. We'll also practice this a lot together. Lastly, folks, on this slide, you'll see that I gave you pHs 1, oops, sorry about that, my pen didn't pen, pH 1, 4, and 9 that were directly aligned with the equivalence points. What if instead I had given you a pH that was equal to pKa? What would the molecule look like in this scenario? So let's try this together, because this one is a bit more challenging. So I'm just going to draw out the molecule without any protons for a second, and then we'll decide what's happening at each. So first, here is where we are dropped down to the x-axis. We have completely passed 1. So the first proton is completely dissociated. If the first proton is completely dissociated, we can represent it just like that, O-. Okay, let's jump ahead now to the third proton. Well, since we are before the third proton, right, we're at 1.5, we haven't even reached 2, never mind 3, we should have kept the third proton. So one of the protons is completely gone, O-, but the third proton is completely kept, should be OH. What about this second proton? You can see that we're right at the midpoint. We are right where pH equals pKa. When pH equals pKa, we already talked about how there is 50% acid conjugate base form, right? 50% acid, 50% conjugate base form. So this last functional group should be 50% O-, and should be 50% OH. So in solution, we're going to have 50% of molecules looking like this, and the other 50% of molecules that look like this. A perfect 50-50 mixture, where 50% of the molecules have completely lost their proton, the other 50% of the molecules have kept their proton, and this will be existing in equilibrium. To wrap up, folks, to our thought experiment, What would happen to us if our blood wasn't buffered and we chugged a bunch of lemonade? Well, thank goodness our blood is buffered. And it's buffered like super tightly with both phosphate, the acid we've been talking about for this series of videos, but also bicarbonate. And we'll learn a bit more about that later, to a pH of 7.4 plus or minus 0.05. So buffered very tightly, regulated very well. That's all for acids, bases, pH, and pKa. This is still an important idea. If pH and pKa is something confusing to you, please make an office hours appointment, because now is the time to get these things straight in your mind. I would say know your functional group pKa's by heart. It might just kind of help you do some homework in this class. No carboxylic acid, no amines, and you got that handout on top hat for you ready to go. Buffers. We also talked about buffers. A lot of what we talk about in this class has to do with buffers because our bodies exist buffered. Additionally, if you've ever done research in a lab that does biochemistry, molecular biology, you've probably used and or made a buffer. With that, I'll leave you with this cat meme. pH is a hard topic. Grumpy cat doesn't like it. Thanks, folks.